Today, one of the main preconditions for the development of any country and its economy are fast, modern roads ensuring swift and safe transport of both people and thousands of tons of goods. Motorways have enabled the movement of people from continent to continent, serving to bring closer together different peoples and cultures, transforming journeys into occasional global migrations to desired tourist destinations. Rushing towards our destinations through tunnels, across bridges and viaducts, we rarely consider the enormous efforts and knowledge the builders had to invest in order to be able to build such structures. Crossing rivers and canyons, negotiating mountains have always posed a special challenge to road builders. And when roads run in the vicinity of protected areas or national parks, extra care is needed in order to protect the environment, which constitutes a still greater challenge to builders. Croatia extends through the karstic belt of the Mediterranean, which abounds in speleological features, caves and holes, as well as tens of kilometers of underground water courses. Consequently, in the course of construction, numerous obstacles are encountered, including caverns, a speleological feature with no natural opening to the surface, and the exploration of which must be carried out by speleologists. According to Dr. Mladen Garasic, professor at the University of Zagreb and a speleologist with 40 years of experience, a good number of them devoted to the study of hundreds of caverns in karst are by no means a rare occurrence. In contrast to holes and caves to which entrances are known and relatively safe, exploration of caverns requires special care, since construction work and blasting render the surface layer very unstable and can result in cave-ins. Statistics tells us that we can expect at least 2 caverns for every kilometer of motorway through the Dinaric karst in Croatia. In about 400 kilometers of motorways, over 850 caverns have been discovered and explored. Fortunately, the most common features lie at an average depth of 25 to 50 meters. The wealth of speleothems, an example, dripstone formations, tells us of the genesis and the hydrogeological functions of a given facility. If at any time of the year there is water in a cavern, the aim is never to fill in the cavern in order to ensure underground circulation and to prevent pollution of underground waters. The real problem facing project designers and builders alike arises when a tunnel is to be built. Even extensive exploration works cannot ensure a positive detection of a cavern in a proposed tunnel. Due to the depth of the surface overhead layer, which in the case of a tunnel can be more than 100 meters, much larger and more complex speleological features can be anticipated. In Croatia, there are several such examples in road tunnels over 5 kilometers in length. Through a small and unobtrusive entrance, larger spaces were reached which extended backwards and beneath the already excavated tunnel. Fortunately, it was not necessary to additionally stabilize the surrounding rocks, since the cavern descended steeply into the depths of the earth. In the same site, we found several interesting speleothems. The hall in question is over 80 meters long and extends steeply and parallel with the tunnel, and through it flows an underground current a few hundred meters long. But the greatest challenge for both project designers and builders was the construction of a relatively short tunnel of 250 meters with a thin overhead layer. An additional complicating circumstance was the fact that the other duct of the tunnel is in function, with thousands of vehicles passing through it daily. As has happened so often before, Dr. Garasic and his team of speleologists were called upon to assist in exploration and documenting of the encountered cavern. Experience to date, combined with the most superficial investigation, made it clear that the hall in question was very large indeed, and which was going to cause additional problems to both project designer and builders. Our group of speleologists is preparing to enter the cavern. The approach to the entrance is being cleared. Entry into the vertical and descent into the hall follows. We sense a large space around us, which our carbide lamps are unable to illuminate.
Lagano, pusta kliče Vukulač. Po Vukulač, kako tako.
Once we have set up a Tyrolean line to be used for lowering our equipment for measuring, photographing, and recording, the remaining members of our team descend.
Super. Super.
We start with measuring and the production of a topographic survey.
Možemo do 23.
Quite obviously, it is raining outside since water is sipping through the cracks into the hall. In addition to this hall, there is an active abyss a few hundred meters from the tunnel, which had been explored during the construction of the first duct of the tunnel, and which is possibly linked to the hall. However, our investigations tells us that the joining canal has caved in. After 8 hours of measuring, we have an insight into the approximate size of the hall. In order to be able to document it as correctly as possible, we also produce photographs with characteristic details. The systematization of documentation and topographic measuring provide us with a map of the hall and its relationship toward the location of the already built and operational tunnel and the one under construction. The main hall of the cavern is over 80 meters long, over 60 meters wide, and more than 40 meters in height, and the tunnels run across its center by height and across 1/3 of its length. In order to span it, a bridge of about 55 meters long would be required. It is becoming increasingly clear that the cooperation between the university and project designers can lead to a solution to complete the tunnel. A month later, when the entrance to the tunnel from the other side is opened, we return to the cavern. The opening of the other entrance, the approach to the hall was somewhat easier. Several alternative solutions have been offered for the completion of the construction of this part of the motorway. Some have even proposed the construction of a completely new tunnel, since they believe the cavern was unstable both in its ceiling and its floor. Ultimately, with the involvement of speleologists, it was decided that the most economic, the safest, and the best solution would be to build a bridge across the hall. Bearing in mind that nobody in the world has so far undertaken such a construction. The bridge would be over 50 meters long and without any additional support pillars. It was necessary to produce a project for the stabilization of the cavern ceiling and assess the quality of rocks in the overhead layer of the tunnel. With that in mind, a 3D animation of the hall ceiling was produced, while boreholes were being sunk from the surface to the hall. Some 10 boreholes between 25 and 30 meters deep were sunk, and all were drilled directly to the cavern ceiling. Samples of bore cores were sent for analysis to the Faculty of Civil Engineering in Zagreb. The strength and the point of fracture of the rock, fissure systems, etc. had to be established, and in order to obtain the required data, all relevant analyses applied throughout the world were used. The result was data on the composition and quality of rocks forming the hall ceiling. Following exploratory and laboratory research, it was possible to begin production of the project and the construction method. The ensuing project involved strengthening the rock in the cavern ceiling by way of numerous anchors and a grid on the surface of the terrain which serves to ensure such strengthening and allows for the construction of bridge abutments in the tunnel to begin.
After the bridge planning had come to an end, it was possible to conduct further building activities in the tunnel. In order to provide good and undisturbed conditions for the construction of both the tunnel and the bridge, it was necessary to develop a project which would ensure the stabilization of the cavern ceiling. The rocks were secured by anchors and a so-called grid, which was constructed into the terrain surface to provide good and undisturbed conditions for the construction of the tunnel and the bridge. Special steel anchors connect the concrete grid-like foundation on the terrain surface with the cavern ceiling and provide additional stability. The anchors were placed in the net-like formation and several hundreds of boreholes were drilled. At the same time, special instruments for measuring the changes of rock tension were placed in some boreholes. These measurements will also be conducted in the extended period after the road is open for traffic. After the cavern ceiling was stabilized with the anchors and the special concrete mass was injected, it was possible to start the construction of grid supporters in the tunnel. First, the additional embankment was built in the cavern to facilitate the access of the construction machines. After these initial preparations, the setup of bridge supporters was initialized on both sides of the tunnel. At that moment, it was possible to begin with the construction of the bridge. Since it was possible for the construction machines to work only within a limited space, the construction was divided into several phases. The sides of the bridge were constructed one by one, after which the concrete tunnel plate was constructed over it. The construction of the bridge was finished in about 1 year. The whole project of the construction of the bridge in the tunnel, in which the renowned experts from the fields of speleology, hydrogeology, tunnel construction, rock mechanics, geotechniques and civil engineering were involved, took almost 2 years. The tunnel with the longest bridge in the world was open for traffic at the end of October 2008.